I'm Suraj and today I'll be presenting our work on spectrum-efficient satellite networks for IoT. This work was done in collaboration with Vaibhav, Tusher, Om, Deepak, and Ranveer. Outdoor wide area networks are a crucial component of the Internet of Things ecosystem, and the demand for wide area IoT is set to explode in the coming years, with an estimated 3.8 billion IoT devices to be connected as a part of it. This demand comes from a wide range of industries, including agri-food, supply chain, oil and gas, and many more. So it is crucial to provide the right connectivity solutions for all of these IoT devices deployed across the entire globe. However, today's terrestrial IoT infrastructure falls short in servicing the scale of IoT deployments that we envision. In a typical terrestrial IoT setup, we need at least a gateway for each network to aggregate data from the IoT devices and upload the same on the cloud through a broadband backhaul. The deployment of gateways involves substantial effort in terms of network mapping, infrastructure establishment, including high-altitude towers, and managing backhaul. Besides, in certain cases, multiple gateways are needed to cover extensive outdoor areas such as farms. And finally, considering that over 80% of the Earth's surface lacks internet connectivity, most of it being the ocean, we can see that relying solely on terrestrial IoT networks to meet the connectivity demands of these diverse industries is insufficient. In light of all of these limitations with terrestrial IoT, there is a new modality that is gaining traction, which is low Earth orbit IoT satellites. The advantage with these satellites is they can enable any device anywhere on Earth to connect seamlessly to the cloud. And there is no more gateway deployment or complex network setups on the user end. Here, the satellites work as the global gateway for the IoT devices on Earth, where the IoT devices will directly send the data to the satellite. Then, the satellite will opportunistically download the data to a ground station when it reaches the ground station in its orbit. Note that these kind of satellites are very small low Earth orbit satellites, and they're known as pico-sats. And before proceeding, let us talk a bit about this pico-sat technology and what is the current state of affairs with this. Is it actually feasible? Is it cost effective or practical? So today, pico-sats present an up-and-coming market with more than a dozen companies like Swarm, Myriota, Astrocast, Forza, and so on, investing heavily in deploying constellations of hundreds of pico-satellites. Considering the huge business potential here, SpaceX also acquired Swarm a year ago. The low cost, small size, and low complexity hardware of these satellites makes them easy to build and launch into orbit, resulting in rapid scaling of IoT picosat networks. A picosat is so small that you can actually hold it in your hand, as you can see in this image here. And on the connectivity front, these satellites utilize narrowband channels for communicating with the devices on Earth, including the ground stations. They're capable of DTS, that is direct to satellite, with the IoT devices on ground, and they use omnidirectional antennas without any beamforming capabilities, and typically they don't even have inter-satellite links. Now, this is one aspect that I want to emphasize here, that is, this direct-to-satellite transmission capability that we're talking about is for regular IoT devices with the constraints such as being power constrained and so on. You don't need the IoT devices to transmit at much higher power, or you don't need to even equip it with high-gain antennas to be able to communicate with these satellites. And this is because low Earth orbit satellites are actually much closer to us than you think. For instance, and I looked this up on Google Maps, LA is slightly farther from here than a satellite would be when it is directly above. So motivated by all these capabilities of picosats, we at Microsoft Research decided to use these for our connectivity needs in farms and other applications that require aggregating data from remote sites. We partnered with Forza, who launched a satellite shown here, which we call MSR-Sat1. We want to note that this satellite was designed by our partner Forza according to industry standards without any design input from us. So we launched the satellite and were waiting for the initialization phase to complete so that we could start receiving data from the satellite to the ground station. The ground station being our partner ground station deployed in Spain. However, we encountered some issues from the first contact with the satellite, and the issue primarily appeared to be related to the downlink communication, that is from the satellite to the ground station. In fact, we started seeing that almost 65% of the packets transmitted from the satellite were getting lost, and this made any sort of downlink communication very hard. So out of desperation to actually start seeing some data from the satellite that we just launched, we started investigating what the issue was here, and in this talk, I will primarily discuss why enabling downlink communication is a hard problem and the techniques we built to enable reliable and robust downlink communications from these satellites. So the primary challenge why downlink data transmission with these picosats is hard is because of the low-cost nature of the hardware used in these satellites. They are severely power restricted because of their size, and they don't have special beamforming antennas. They just have these regular omnidirectional antennas. So this means they can't achieve high SNRs, and they end up having very low link budgets. In fact, in our measurements with our satellite in orbit, the received power level from the satellite was so low that it was typically always below the terrestrial interference level or even the noise floor of a receiver. Second, because these satellites have these omnidirectional antennas, they end up with a very large footprint on the Earth's surface, and as a result, with multiple of these orbiting satellites, the ground station will fall under the overlapped footprint of multiple neighboring satellites, and this leads to a lot of inter-satellite interference and collisions, which in turn reduces your spectrum efficiency. So to demonstrate why these challenges are so hard to work with in the real world, let me start with an example. On the left side here, we emulated the signal that we expect to see from MSR Sat1, and these signals use the 2 GFSK modulation. So if we transform this signal in the time domain to the frequency domain, we see 2 clear peaks with the exact frequency deviation that we expect to see given a GFSK modulation. Now on the right hand side is the actual time domain signal that we received from our satellite in orbit, and over here you can see that firstly, of course, the signal is super noisy, but also the fact portions that you see here are not signals from our satellite. These are in fact the high energy noise from terrestrial sources of interference. And if we were to transform this to the frequency domain, you can see that there is no clear peaks in the frequency domain as you would expect for a GFSK modulation. Okay, so just for the sake of it, let's see that if we try to run the standard LoRa packet detection on this noisy time domain signal, do we even get anything? So again, on the left, we have the real signal received from MSR Sat1, and on this, we run the classic packet detection technique. Now, typically how packet detection works is, you have a known LoRa preamble, and you keep correlating it with different moments in the time domain signal, and whenever you see in the peak in the correlation output, that means there's a packet there. So we run the classic packet detection technique, but as you can see here on the right, the classic approach exhibits very poor performance, and there are no clear peaks over here corresponding to packet start, even though we know there are packets here, and this is because the packets are just buried under very high noise and terrestrial interference. Okay, so it turns out that even if the packet is being received by the ground station, it is so weak that we are not even able to detect its presence in our signal, let alone being able to decode it. In addition to this first problem of low link budgets, we also have the second problem of collisions and spectrum inefficiency. Because the footprint of these satellites are huge, the same satellite falls under the footprint of multiple satellites, and this occurrence is very common. So if more than one satellite transmits, then there will be a collision, and the ground station can't receive anything. Keep in mind that collisions are going to be common because standard medium access techniques like carrier sense don't work for satellites, since these satellites can be quite far apart and can't hear each other's transmissions. So to address these issues and to enable a spectrum efficient satellite network for IoTs, we introduced Spectrumize in this paper, a new class of techniques that use Doppler shift, caused by the satellite's motion as a unique signature for packet decoding and detecting. And this works even in very low SNR conditions or even in the presence of collisions between multiple transmitting satellites. To explain what the concept behind this is, I will show this through an example. So this is the key opportunity that we're going to leverage here. Each satellite has a unique motion relative to our ground station on Earth, and as a result, it introduces a unique Doppler signature in the signal that it transmits. You can see an example of such a Doppler shift here, and the interesting thing is these shifts can be very precisely calculated beforehand because we know the satellite orbits, and we will leverage this to our benefit. That is, we will use these unique Doppler signatures as 5-layer CDMA codes. Let me show how leveraging such Doppler shifts can help us solve our two challenges. So over here, you have this packet transmitted by the satellite where there's a preamble portion and there's a data portion. Now, there is one detail that I won't get into too much here, but keep in mind that with these picosat transmissions, typically when a satellite transmits, it will transmit a sequence of packets, one after the other. So a periodic packet train with a predefined number of packets, in our case about 10 packets, as shown here. So now, because of the Doppler shift induced by the satellite's motion, the transmitted packets actually are frequency shifted following the Doppler signature, as you can see on the screen here. Now, what happens with traditional packet detection techniques, right? They take a single preamble shown by the orange packet here, and they keep correlating it with the received signal by shifting the preamble to different positions of the received signal, and it measures the correlation value. Wherever you find a strong correlation peak, that means a packet exists there. However, traditional packet detection techniques don't account for the Doppler shifts because in traditional terrestrial networks, there is no Doppler to account for. And as a result, by using these traditional techniques for packet detection, you do not see any correlation peaks, as you can as well see on the graph over here on the right. So clearly, one thing that you absolutely must do is account for Doppler shifts. And because I know the orbit of the satellite, I can measure this estimated Doppler shift at each time instant, and I can add that corresponding Doppler shift to my preamble packet during correlation. So this modified correlation process will look somewhat like this, and by doing this, it does improve our packet detection performance, but it still has multiple comparable peaks, and often this leads to false positives. So even this is quite not enough. So to account for this, we actually move from single preamble correlation to correlation with an entire preamble train. Now this is again possible in the context of satellites because recall IoT satellites always send a periodic train of packets once they capture the channel. So we can have this train of preambles here where each preamble is shifted according to the corresponding Doppler shifts, and if we correlate this train of preambles when it is perfectly aligned with the start of the packet train and the real signal, we get this big peak as shown here. And if we were to shift the train of preambles and then correlate again with the real signal, we see a low correlation peak since in the real signal, the train of packets do not start at this point. So using this Doppler corrected preamble train, we can detect packets being transmitted from a satellite even in very low SNR conditions because now we are leveraging multiple preambles to get a high correlation score. So having gone over our solution for the first challenge, that is very low link budgets, let me quickly talk about the second challenge, and interestingly the same technique works here as well. The second challenge being that we observe a high number of collisions between transmissions from multiple satellites, and because of these collisions we are not able to resolve packet collisions. To explain this at a very high level, we have these two satellites, the blue one and the green one, and because the location with respect to the ground station is different, the Doppler signatures with respect to the ground station are also different. And as a result, the respective packet trains will have different Doppler signatures encoded into their frequency shifts. So similar to how CDMA codes work, we can leverage these unique Doppler signatures and try to find the start of the blue packets by correlating with a preamble train that is shifted as per the blue Doppler signature. This is shown here in the orange preamble train. This way, the correlation score will be high when we align the preamble train with the start of the blue satellite signal, but it will be low from the green satellite signal since its Doppler signature is different. Of course, this is all at a very high level, and we have more details in the paper. We also discuss how our system handles errors in estimated Doppler shifts, hardware imperfections, and so on. So I have given you an overview of how our Doppler signature technique helps solve our two challenges. Next, let me move to our results and evaluations. So as mentioned previously, we launched our own satellite in partnership with FOTSA, and most of our results and evaluations in the paper are from measurements from this real satellite in orbit. In the first result, I show the performance of our technique against baselines for the task of packet detection, that is figuring out if a packet is there and what its start time is. F1 score is a measure for how good a prediction model is, where high F1 score means low false positives and low false negatives. Our baselines are techniques like using just a single preamble, or using single preamble with Doppler, or a preamble train without Doppler, so essentially an ablation study. And here we can see that Spectrumize can improve your performance of packet detection by up to 3 times compared to your different baselines. In the next result, I show Spectrumize's ability to decode packet collisions among multiple satellites. So in this experiment, we configured 2 satellites in orbit to collide at our satellite partner's ground station. And this graph shows that even under collisions, Spectrumize is able to correctly decode both collided packets with over 80% accuracy on average. In comparison, our baseline CIC, which does collision resolution for LoRa without accounting for Doppler shifts, on average only has 30% accuracy. In addition to these results, we also have more results in the paper that talk about how robust Spectrumize is to errors in the Doppler signature estimations, synchronization issues like CFO, SFO, and so on. So this brings me to the end of the talk, and I'm happy to take questions now.